Hello, please confirm that you can hear me. Hello, can one of you please confirm that you can both hear me and see the presentation?
Yes, sir.
Both are all right, fine, thank you very much. Um, so today I will just briefly recall what we begin by briefly recalling what we considered in the last class. So I hope all of you are able to see and hear me, the presentation. And just a minute, please. Just 1 minute, please. Okay, so in the last class, we began the discussion on nonlinear autonomous systems. And I mentioned, I gave the example of the logistic equation, which applies second order of nonlinearity. Now, if you recall an earlier discussion which I held when we talked about the first order of nonlinearity, I mentioned that all of these autonomous systems, first order autonomous system, as in dx dt is equal to fx, dx dt is equal to fx, it does not have a turning point. A turning point corresponds to a situation when you have a zero first derivative in x. Dx dt will be equal to 0, but the second derivative d2x dt squared will not be equal to 0. So that sort of a situation does not happen for this kind of a system. If dx dt is equal to 0, then d2x dt squared will also be equal to 0. As a result, these functions do not have any turning point in the xt graph. So in the last class, look at this equation, dx dt is equal to ax minus bx squared. A and b are both positive quantities. And in the early stages, you start with a small but non-zero value of x. If you start so, small non-zero value of x, then gradually, if you just look at this equation, let us, not get into too many complications. A and B are positive quantities. Initially, x is a small non-zero positive number to begin with. Okay, which means a into x will be a positive number. And x squared, being of the square order of a small number to begin with, can be ignored against the lower order. So initially, your equation will almost be like dx dt is equal to ax. Such an equation will show an exponential growth behavior. Why growth? Because a is positive, x is also positive, therefore dx dt must be positive. And so the slope will be positive, the derivative, the gradient will be positive. And I told you that this sort of a system does not undergo a turning point, meaning that once it is positive, dx dt uh, will not be negative again. A turning point is a situation whereby the dx dt changes sign. Through a turning point, dx dt changes sign. But this sort of a system does not have any turning point. And so where the first derivative vanishes and the second derivative also, for a turning point, that's the requirement. First derivative 0, second derivative non-zero. Not always, by the way, not always. There are exceptions also, but generally speaking. So here, in that sort of a situation, you will, in fact, these exceptional situations I shall also touch upon later. Maybe I will have the time to do that. But for the time being, let's just say that this sort of a system does not have a turning point, and so you will keep growing. What will be the growth? Will the growth be like? In the last class, we had a long discussion on rescaling, integrating by the method of partial fractions, as has been written over here, setting initial value and realizing that the initial value will not be equal to 0. I discussed in the last class why it should not be equal to 0. And then under various limiting conditions, we saw approximating circumstances. What we found was that when capital X is equal to half, or that is to say small x is equal to the limiting value by 2, then at that point the second derivative changes sign. Let us see what do I mean by that. Here is the graph. You start for small values of time, starting with a small enough non-zero value of x. It would look like that your logistic equation dx dt is equal to ax minus bx squared is behaving almost as if it is only ax, as if there is only ax on the right hand side. Bx squared is an insignificant quantity comparably. So dx dt is almost equal to ax, meaning a robust early exponential growth. Along this path, dx dt is positive. Follow carefully. d2x dt squared is also positive. Fine. Then at this point, where k is equal to 2, I'm sorry, x is equal to k by 2. This is x, this is t. Where x is equal to k by 2, at this point, the nonlinear behavior starts kicking in. So that is the nonlinear time scale, TNL. NL as in nonlinear. What do I mean by nonlinear behavior starts kicking in? Let us try to see. Uh, this is the equation dx dt is equal to ax minus bx squared. Now x has grown to such a value that you can no longer afford to ignore the effect of this bx squared, but it has got a minus sign. With this minus sign, it is now applying a brake on the growth. So without this thing, dx dt is equal to x will have show an exponential growth, but this thing is now applying a brake on the growth. Why a brake? Because of the minus sign. So that is shown in the graph. So at this point, the negative sign causes a break in the growth. If bx squared, that term were not to have been there, then this graph would have followed this dotted line track straight on without limit to any growth. But at this point, the break in the growth happens. So when the break in the growth happens, what is the feature at this point? At this point, the second derivative will momentarily, second derivative, d2x dt squared, not dx dt. Dx dt will always be positive if you are a little mindful and recall your lessons of calculus. I hope you are able to understand this point clearly. All along this path, the function is growing. Therefore, dx dt is positive. But along this path, the function is growing at an increasing rate. And from here, thereafter, the function is growing at a decreasing rate. And so what is the signature between these two phenomena? I mean, the distinction between, how will you mathematically make a distinction between these two phenomena? Here is the answer, that d2x dt squared will momentarily be 0. At that point, dx dt will not be equal to 0, but d2x dt squared will be equal to 0. If that were to happen, sorry, just a minute. If that were to happen, then the function will change its concavity. That is the technical phrase that is employed. The function will change its concavity. And how will you know? What is the point where concavity changes? Second derivative vanishes, but the first derivative will not. First derivative is non-zero. Second derivative vanishes. And the condition for the vanishing of the second derivative is capital X is equal to half from this condition, which I discussed in the last class. If capital X is equal to half, small x is equal to k by 2. So because capital X is equal to small x by k by 2. So you can now see at this point, the slope of the function is non-zero. It still has got a finite slope, but the second derivative at this point is momentarily 0. Thereafter, the second derivative will become negative. And here, the second derivative along this track will be positive. At the point where the second derivative will be 0, capital X will be equal to half and small x will be equal to k by 2. So that, and this is growth at a decreasing rate. So this is important. I told you, you are starting with a small value of x. How small? Well, preferably less than k by 2. K being, and how will you know what is k by 2? You can know k by knowing a and b, which will be supplied to you in the equation. Somebody has supplied you the equation dx dt is equal to ax minus bx squared. and A and B values will be provided to you. And so knowing the A and B value, you'll immediately know K. As soon as you know K, then to set an early exponential growth, robust early exponential growth, you'll set an initial condition of K by less than K by 2, significantly less than K by 2. So X naught will be significantly less than K by 2. And then it will keep growing till there will be a stage when x will become equal to k by 2. Thereafter, the growth will have a saturation behavior. Without this nonlinear term of bx squared, this curve would have followed this dotted track and kept on going to infinitely large values in the long run. But that doesn't happen. So when the function goes to infinitely large time, when time goes to infinitely large value, the function will go in converge to the ceiling of k equal to a by b. That is what happens. And then eventually the growth will stop when this slope, this is gradually going to flatten out. And at infinity, at t equal to infinity, this dx dt will be equal to 0. And but when t is equal to infinity, dx will be equal to k. The limiting value will be reached. And that is where the growth will stop. I mentioned to you in the last class, I hope you recall that yeah, I mean, see, these notes have been supplied to you. So you better start working these things out. They're all there in the Google Classroom. Yesterday, when I sent the class link record, I also verified that I asked you to confirm. Just check for yourselves that everybody is getting the mail only through the BTech CS 2020 batch ID. Hereafter, I shall no longer send you mails through the entire class ID, like BTech or whatever, section A, section B, all those things, or ICT, etc. No. Now you will get mails exclusively through your group ID, and you have all been admitted into the classroom also. I hope everybody has verified that fact. And so hereafter, you should also be using all the material that has been put up in the Google Classroom. Incidentally, if anybody knows somebody named Amol Manilal Patel, ask him to accept the invitation in Google Classroom, because soon enough I shall ask you to form your lab groups. Right, by next Monday we shall have a discussion. Anyway, at the end of the class I'll touch on these points. So by now the group has been formalized. Anyway, so I hope you have understood this discussion of a nonlinear equation. This is also a part of your theory package, the theory problem set, mathematical theory problem set that I have supplied to you. You should look up that. And this logistic equation, this dt of dx dt is equal to ax minus bx squared is one of the problems. So you can use this solution. There are some errors also, but there is in your Google Classroom under the mathematics theory folder link, you have a set of corrections also. So I hope you should not have any difficulty understanding all that. Anyway, so let's now move on to discussing another nonlinear equation. Hopefully we should be able to wrap up all the math discussion today and soon enough start the physics discussion, because you'll be doing computational physics, not computational math. Here's another nonlinear equation. The previous equation was ax minus, the nonlinear equation previously was ax minus bx squared. What do I mean by nonlinear? By nonlinear, I mean that this function fx is nonlinear. If you did not have the bx squared, then it would have just been a linear equation. Dx dt is equal to ax. The right-hand side would have just had the first power, but it has a second power. Prior to this, in the previous set of notes, I discussed a linear set of equations where we had a plus minus bx. That is a linear equation. That equation will be important physics-wise. So go through all those notes and the math theory problem carefully. Of course, you'll also have to do the numerical work. Why it will be important? Because when you look at objects falling through a long liquid column, it is governed by an equation like that. Then in the geology also, that sort of a problem happens. There are various other non-physics or non-natural contexts, like I mentioned to you, Duckworth-Lewis method for calculating run rate in cricket matches, that is there. The logistic equation that we have in front here, it has got application in estimating the growth of population. It was in fact in the context of population that the name logistic was introduced. Also, the term which I mentioned in the last class at the end, carrying capacity, these terms come from the concept of population dynamics, the subject of population dynamics. Now we are looking at another equation, a nonlinear equation, because the right-hand side has no power of, the highest power on the right-hand side is square power of x, right? I mean, see, the nonlinear equations can be of various types. I mean, I'm just discussing a few very simple nonlinear equation, ax minus bx squared, a minus bx squared, that sort of a thing. You say that what is the point? Well, I mean, if I have to discuss, there's a whole bunch of nonlinear equations. Yes, indeed, there is, but it's still okay to discuss these things. At least you'll get a flavor of handling nonlinear equations through these simple examples. Like, of course, in your math theory problem set, I gave you a nonlinear equation like dx dt is equal to cos squared x, right? So that's also a nonlinear equation. So you can have various nonlinear contexts. Anything that is not in the form of a plus minus bx is nonlinear. So really, I mean, you have infinite number of possibilities, in fact. But well, anyway, these are some helpful examples to begin with. And also we have to keep an eye on the physics concepts. Just a while ago, I told you that a system like a minus bx, not x squared, a minus bx, there are physics contexts of that sort of a mathematical system, such as particle falling through a liquid column, geological problems, right? So such systems obey equations like a minus bx. So, but here we have a system a minus bx squared, and this sort of a system is for a particle that falls through a gas column, like a parachutist falling through air, right? uh, Obeys this kind of the square behavior is important. We shall see that thing whenever objects are trying to move through air against air resistance. Usually it is the square power that is important. We shall see with some proper physics examples soon enough. Anyway, there's one thing that I'd like to make you remind you, is that with A and B being positive, what is the requirement on the initial condition? I hope you will be able to recall that in the last class I said that if you have a system like dx dt is equal to ax minus bx squared, then as soon as you set x equal to 0 on the right hand side, dx dt will be equal to 0. So at t equal to 0, if you set x equal to 0, dx dt will also be equal to 0. Thereafter, there will be no growth for this system, right? There will be no. So anything that is rate is proportional to the state, rate as in ddt of x, and state as in x itself. Whatever value you have, your growth rate is in proportion. Whatever value of x you have, your growth rate, that is dx dt, is in proportion to that, right? So if that sort of a situation happens, then the initial value must not be 0. Because if both x is equal to 0 and its growth is also equal to 0, then you have nothing. You have nothing to begin with, and dx dt equal to 0, meaning you're not going anywhere. So you must start with a non-zero value of x, and then you will grow. Otherwise, you'll have what is known as a trivial solution. I mentioned this whole idea of a trivial solution, where both x is equal to 0. But if you have a situation where even if you set x equal to 0 at t equal to 0, you'll see that dx dt will still be non-zero. See, if x is equal to 0 here, dx dt will still be equal to a, which is a positive number. Therefore, even with a non-zero value of x, you will be able to grow. I'm sorry, with a 0 value of x to begin with, you'll be able to grow. I also mentioned to you in the last class that dx dt is equal to ax follows geometric progression, whereas dx dt is equal to a follows the arithmetic progression. Arithmetic progressions can start with 0 values, because the next step size will just be added to 0 and you'll get a non-zero value. But geometric progressions can't start with 0 value. Why not? Because the next step will be multiplied with the previous value that you began with. And if the previous value is 0, then you are still 0 even after the next step. And once you start with 0, Multiple times you can multiply 0 with any number of steps that you have, you'll still get 0. So geometrical progression, the progression is multiplicative. Arithmetic progression, the progression is additive. Additive progression can become non-zero even if you start with 0, but the same thing doesn't apply for geometric progression. Be clear on those things. Anyway, so we shall just now apply the old ideas with which we are familiar. We rescale this equation. Rescale it as, take the a to the left-hand side in the denominator. So you'll have 1 upon a dx dt is equal to 1 minus x squared by by a by b, I'm sorry, x squared divided by a by b. Okay. Now, so we define capital X is equal to small x divided by the square root of a by b. Okay. So if that is so, then small x is equal to capital X into this constant square root of a by b. You substitute this small x by this capital X times this multiplicative constant square root of a by b. And square root of a by b, and then with this a in the denominator, you will get a new rescaled time. You can check it by for yourselves. It shouldn't be a challenge. Capital T, you're defining as square root of AB into T. Hereafter, this equation becomes a parameter-free equation. D capital X, D capital T is equal to 1 minus x squared. Then you separate variables, take this 1 minus x squared to the left-hand side and T only to the right-hand side. Again, it's the same thing, method of partial fractions you apply. 1 divided by 1 minus x squared is the product of 1 minus x and 1 plus x is partial fraction a divided by 1 minus x plus b divided by 1 plus x. Next, you multiply this equation throughout by 1 minus x into 1 plus x and you'll get this. So when x is equal to 1, capital X is equal to 1, 1 minus 1 will be 0, and 1 plus 1 will be 2, so capital A will be half. And when x is equal to minus 1, 1 minus 1 will be 0, and 1 minus of minus 1 will be 2, therefore b will be equal to half again. So by the method of partial fractions, you have set the values of capital A and capital B, and so your equation is now half dx by 1 minus x plus half dx by 1 plus x is equal to integral dt. Integrate. Just this 1 minus x business, I'm applying a slight trick over here. Minus and minus will become plus, and I'm making the variable over which the integral is to be performed as minus x. Once I have that, thereafter it's a simple task. This part will integrate to give you log of 1 plus x. This part will integrate to give you minus log of 1 minus x. 2 dt will give you 2 times t, and the integral constant I'm writing as log c. And 2 times t I can write as log of e raised to twice t. Thereafter, everything is a log. You do the usual procedure, gather all the terms with the log on one side in x and the other side in t, then take the anti-log, and this is what you'll get. 1 plus x divided by 1 minus x is equal to c into e raised to 2t. Now you can see I mentioned to you that here you can afford to apply the initial condition that at t equal to 0, x is equal to 0. That is what we have done here. At t equal to 0, that is to say capital T is equal to 0, because capital T is just a constant times small t. Small t will be 0, capital T will be 0. Similarly, capital X is just small x divided by a constant quantity, non-zero constant, because a and b are both positive numbers. And so if small x is 0, capital X is also equal to 0. So we can afford to apply that initial condition. Capital T is equal to 0 and x is equal to 0, both for the uppercase in time as well as in x. Once we have done that, then we can check for ourselves that this will be 0, this will be 0, and t will be 0. So 1 plus 0 by 1 minus 0 will be 1 is equal to c e raised to 0. E raised to 0 will be 1, therefore c will be equal to 1. Next is that we shall make x the subject of the formula. Here we have got a whole mixture of x on the left-hand side. We will write x as a function of t in the closed form. So how? 1 plus x is equal to c is equal to 1. So e raised to 2t minus capital X into e raised to 2t. Then we take this one to the right-hand side and this minus x e raised to 2t to the left-hand side. take x and x from here as a common factor, capital X into 1 plus e raised to 2t is equal to e raised to 2t minus 1. And capital X will be equal to e raised to 2t minus 1 divided by e raised to 2t plus 1. Okay. Now, what I'm doing is that a slight trick. What is the slight trick? I'm multiplying and dividing. Multiplying both the numerator and the denominator with e raised to minus t. When I multiply e raised to 2t with e raised to minus t, I'll get e raised to t minus of e raised to minus t. Then same thing here, you follow carefully, same thing here, e raised to minus t into e raised to plus 2t will be e raised to t plus of e raised to minus t here. And then I'm dividing both the numerator by 2 and the denominator by 2. Why have I done that? Because there is a defined function for that. The numerator is e raised to t minus of e raised to minus t by 2. And the denominator is e raised to t plus of e raised to minus t by 2. This function is the sine hyperbolic function. And this function is the cosine hyperbolic function. You may not have directly worked with hyperbolic sine or cosine functions, but at least you should be familiar with these forms. This sort of a form appears also in complex numbers. Sine of theta, just remember, no hyperbolic business, just ordinary sine theta. Sine of theta is equal to e raised to I theta minus e raised to minus I theta divided by 2. Why? Because e raised to I theta is equal to cos theta plus I sine theta, right? Divided by 2 times I, right? And similarly, cosine of theta will be e raised to I theta plus e raised to minus I theta divided by 2. You can just check what is e raised to I theta. E raised to I theta is cos theta plus I sine theta. What is e raised to minus I theta? That is also cos theta, but minus I sine theta. When you add the two, e raised to I theta plus e raised to minus I theta, you'll just have 2 times cos theta. 2 times cos theta by 2 will give you cos theta. So these hyperbolic sine and cosine functions actually have the same form as the way you can write the trigonometric cosine and sine functions in terms of exponential functions, but having a complex argument. Here we are having real numbers, so we write it in terms of something known as hyperbolic functions. So anyway, but the same principle holds. This is sine hyperbolic, this is cos hyperbolic. Just like sine theta by cos theta is tan theta, so similarly, sine hyperbolic by cos hyperbolic can be written as tan hyperbolic. So capital X is equal to tan hyperbolic of t. That's the definition. Sine hyperbolic by cos hyperbolic is this thing. Now we go back to the original variables with which we started. Capital X is equal to small x by square root of a by b. So that is what we have. And capital T is square root of ab into small t. So this is your final solution under this initial condition. Okay, let us now see. I mean, you can plot this function. Incidentally, there are various functions that are applied. All this kind of a nonlinear function and the logistic function, they have a similarity of appearance. Let me just mention this thing to you also. Certain similarity of appearance. Let us see what is it like. Now we shall have to plot this function by hand. By hand, we'll plot this function. So we will look at this tan hyperbolic business a little more closely. What is the small time behavior? Small time behavior is that when t is equal to 0, e raised to 0 minus of e raised to 0 will be 1 minus of 1, 0. So x will be equal to 0. That corresponds to the initial condition. What if t is a small number, slightly greater than 0, but much less than the scale in the problem? And what is the time scale in this problem? This is the time scale in this problem. You notice once again, I mentioned to you in the last class that if you have an exponential function, its argument must be dimensionless. What is the argument of these exponential functions? All these 4 things, 2 things that you have, e raised to plus t and e raised to minus t. T is the argument, capital T that is, and it must be dimensionless. But capital T is defined as square root of AB into small t. Therefore, square root of AB into small t must be dimensionless. But t has the dimension of time. Therefore, to overall be dimensionless, square root of AB must have the dimension of inverse time. So t divided by 1 upon square root, t divided by 1 upon square root of AB will give you, or AB raised to minus half, t divided by AB raised to minus half will be a dimensionless quantity. So let's say that our time, small t, is very much less than AB raised to minus half, right? In that case, all these exponential functions, if we break them open, e raised to plus t and e raised to minus t, here we are. E raised to plus t will be 1 plus t squared by factorial 2, etc., infinite series. And similarly, e raised to minus t will be 1 minus t plus t squared by factorial 2, again infinite series. The odd powers will pick up a negative sign. The even powers will be as they are before. Now, capital X is equal to e raised to t minus of e raised to minus t and e raised to t plus of e raised to minus t. These two twos, division by 2, they will cancel anyway. So that is what we are writing. E raised to plus t minus of e raised to minus t, e raised to plus t plus of e raised to minus t. Now, here in this equation, let us see what we can do. I have written this series here, I've written this series here, and immediately because of this minus sign, I will realize that all the even powers will cancel. 1 here and 1 here will cancel. T squared by factorial 2 and t squared by factorial 2 will cancel. And we will just have the survival of the odd powers. Here you will have t, and here you will have minus of minus t. So that will be 2t, 2 times t in the numerator. What about the denominator? You have 1 plus t plus factor t squared by factorial 2, and this 1 minus t plus t squared by factorial 2, all that way going all that way. And so this time the odd powers will cancel because of this plus sign. So t and t will cancel. 1 survives. 1 is not an even number. I mean, see, you have the square power, and 1 is like the zeroth power. Any number, any non-zero number that is raised to 0 is 1, right? So this is the zeroth power. This is the second power. So all the even powers survive, although 0 should not really be considered an even number, but it's part of the same sequence in a sense. So basically 1 plus 1 will be 2, and then you'll have t squared by 2, and you have t squared by 2. When you add the 2, you'll just get t squared. But since capital T is very much less than 1, against 2, you can neglect the t squared in the denominator. So approximately this thing will be 2t by 2, and that's approximately t. And so small x, once you have capital X here, small x will be equal to, as per this formula, root of a by b into tan hyperbolic square root of ab by t. This part has become now, this tan hyperbolic part, that thing has become a into t. So, sorry, root of ab into t, because it's capital T, right? So you're just writing all that and make a cancellation. This should be small x, not capital X. In my hurry, I wrote capital X. It's there in your table of corrections. The error has been corrected. You can just check it up. I'll also upload some corrected notes. I mean, some more errors have been discovered through this course so far. So I'll correct those and upload the notes. So here you have capital X is equal to AT. Sorry, small x is equal to AT. That is the early growth is linear. What about the late growth when t goes to infinity? You have this equation. Now this equation, which is this, I'm doing something more. I'm multiplying both the numerator and the denominator with e raised to minus 2t. So this will be 1. This will be minus of e raised to minus 2t. This will be 1 again, and this will be plus of e raised to minus 2t. When capital T goes to infinity, e raised to minus these two numbers will go to 0, and capital X will tend to 1. So when t goes to small infinity, small t goes to infinity, capital X going to 1, meaning small x will tend towards square root of a by b. This will happen for t very much greater than negative square root, 1 upon square root of ab. So here is the plot. Early growth is linear, starting from 0. Then, when you come to this capital T equal to 1 business, or small t is equal to ab raised to minus half, that part, thereafter, there is a different kind of dynamics. The same system will show different kind of dynamics. Why at capital T? Because this linear behavior, this result has been obtained under the approximation that you can neglect the higher powers of T. That you can do only when your capital T is very much less than 1. But when capital T is comparable to 1, this neglecting of the higher powers can't happen, and there will be deviation from the early growth, early linear growth. But overall, this sort of a system will not have any turning point. That's the nature of first order autonomous systems. Dx dt is equal to fx. Therefore, once grown, it will keep growing. Early growth will be linear, and thereafter, beyond this point, it will start saturating towards the limiting value of square root of a by b, or a capital X is equal to 1. So there is a little comment over here. The comment is that d dt of x is equal to a minus bx, not a minus bx squared. Here we are using the nonlinear equation a minus bx squared. In the last class, we talked about a minus bx, the linear system. There the saturation will happen when dx dt is equal to 0. So x will be equal to a by b. Saturation meaning when the slope of the function finally becomes 0. That will happen when t goes to infinity. So this function will become, will no longer grow, flatten out, but not fall down. Right, at infinity you have reached, there is no further space for you to grow, so it will not turn around. Infinity means that's the end, but the end is infinitely far away. Now, for this kind of a system, dx dt is equal to a minus bx squared. When does saturation happen? Again, when dx dt will be equal to 0. That is to say, touch this horizontal dotted line. What is the condition for that? Dx dt is equal to 0. On x, the condition will be a minus bx squared is equal to 0. Therefore, x will be equal to square root of a by b. At saturation, that is happening. But you notice that this is a square power of nonlinearity. This is the first power of nonlinearity. When x goes to large values, the square power of nonlinearity becomes more dominant comparable compared to the first power of nonlinearity. As a result, the limiting value of x for the square power of nonlinearity will be less than what it is in the case of the first power. This will quench the system or saturate the system at a smaller value of x, namely square root of a by b. But this will this will be saturated at a larger value of a by b. So that is how it is. Anyway, so as I said, I just would like to touch upon a point. You look at this growth. Early growth is linear, and then you have saturation. This function here will also show something similar. Early growth will be linear. You look up the old notes, the previous set of notes, mathematics theory MT set 2. MT set 2. You look at the set of notes and you will get what I mean. And then again, they will appear, it will saturate. So in terms of appearance, both show the same qualitative behavior, meaning that early growth linear and then there's a long time saturation. That is different from the logistic equation where the early growth is not linear, it is an exponential early growth, which means that it must start at a non-zero value. Both this function, this equation and this equation can afford to start at 0, because as you can see, when I set x equal to 0 on the right hand side, I will still get a non-zero dx dt, which will be both equal to a, meaning that even if I don't start with anything, the system will still grow out of it. But here, if the system doesn't have a non-zero value to begin with, then it will never grow, because this is a geometric growth, product multiplicative progression, right? So the early growth is exponential, but then there is a saturation in the late stages. So different kinds of systems show different kind of behavior. These are two broad classes of problems. There could be other classes of problems, but you just keep a watch for the early growth trend. Dx dt, is it equal to 0 or not equal to 0 when x is equal to 0, at t equal to 0? That should give you the clue as to what the initial condition should be like. in many of your physics problems, see, I mean, if you are a physics person and you're trying to solve something that no one has done it before, so nobody is going to give you a problem sheet saying that here you take this step size and here you take that initial condition and all that. So these are matters of judgment. If you look at the equation, if you look at a system, then you should be able to find what is going on. For instance, I'll just simply give you an example. Population dynamics. You can't have a population coming out of nowhere. It has to start with some initial members of a species, right? Which means that immediately you'll realize that population dynamics can't be identified by this kind of a system or this kind of a system. A population dynamics, and it so happens, is better described by this kind of a system. But then there will be also a growth saturation in the long run. Compound interest. If you don't put money in the bank, there will be no growth for you. Early exponential growth, compound interest growth happens like this. I shall just discuss these things. So basically, it's again a matter of judgment. You have to do these. Some good practice gives you good insight in these problem-solving techniques in your lab. So far, I have been giving you initial conditions and step sizes and all that, but occasionally, maybe later, sometime in life, when there will be no sir to tell you what to do, you yourself will be the sir, then you will have to decide what you have to do. So this, I hope this trading will be useful for you somewhere, someday. Now comes a very important thing. Numerical errors while integrating. For long have I been telling you that step size is very important when you calculate something, when you evaluate something. Let us see, what do I mean by that? Here is something, numerical errors while integrating. How should you determine the step size? First, let us begin with just now I told you, how will you make an educated guess about an initial condition? So you just have to look at the form of the equation, look at the form of the physical system, and make an initial educated guess about the initial condition. Whenever you do an numerical integration, you have to do quite a few, you have to start with quite a few things. What is the initial condition? Without it, you can't integrate. That's the first stepping stone. Then what is the step size? That's the first step. Then what is the step size? After you have from your starting initial condition tells you what is your starting point, right? Then the step size will tell you how big a stride you will take. So all these things. So now comes something important about the step size that you have to take. Here is the discussion. Consider a simple differential equation. d dt of x is equal to lambda into x. This is x, although it is looking like k, but it is x. Okay. With the initial condition, at t equal to 0, x is equal to 1. Integration is a very simple thing. You should be experts by now. dx by x is equal to lambda dt. Integrated will give you log x plus constant log x naught plus log e raised to lambda t. This is lambda t, but I'm writing it as log e raised to lambda t. So x is equal to x naught e raised to lambda t. That is my integral solution. And initial condition when t is equal to 0, x is equal to 1 as per this. Follow this discussion with deep attention. This whole discussion. T equal to 0, x is equal to 1. Therefore, x naught will be equal to 1. 1 here and e raised to 0 will be 1. So x naught equal to 1. This is my solution. X is equal to e raised to lambda t. Now, I have not so far told you what is lambda. Lambda is a number, right? Immediately you should be able to realize, looking at this number and being mindful of the discussion that I have had so far, we have had so far, that lambda must have the dimension of inverse time if t should have the dimension of time, because lambda into t must be a dimensionless product, so that you can make it the argument of an exponential function. Why so? Because the exponential function is an infinite series, so you can't have a dimension or time or length or whatever. If t has a dimension of time, then the next thing is time squared, the third thing is time cubed, like that it goes on. What is that? Or if t has got the length dimension, length, you add area to that, then the next thing is volume. Have you ever done such a thing in physics? No, of course not. So there is something called dimensional compatibility. So argument of all these infinite functions, e, log, sine, cos, they must be dimensionless. That will give you a vital clue as to what is the scale of the system. In this case, the scale of the system will be 1 upon lambda of that order. We shall see soon now. Anyway, so let's see. Now, suppose lambda is a negative number. So it will be a negative number into real positive time. Time can't be negative. So negative number into positive time when t goes to infinity, this product will be minus infinity. If it is minus infinity, e raised to minus infinity will make it go to 0. Therefore, when t goes to infinity, x will go to 0 if lambda is negative. All of you, please follow with due attention. This will be very important for your lab work. Now we apply the Euler method. What is the Euler method? Euler method is, I mean, just taking the different derivative, all this thing. Dx dt is equal to lambda x. Instead of dx, I'm writing delta x. Instead of dt, I'm writing delta t. And then this is what we have got. Just taking the derivative and writing it in terms of a differential. So that is what it is. Delta x, sorry, writing it in terms of a variation. Variation, small change. Delta x is equal to lambda x into delta t. And what is delta x? Delta x is x n plus 1 minus xn. And lambda x will be lambda xn into delta t. So xn plus 1 is equal to xn plus lambda xn delta t. You are quite adept with Euler's method by now, I hope. You have gone through some lab discussions also. So there we are. This is the formula that we have. Xn plus 1 is equal to xn into 1 plus lambda delta t. And so x1 is equal to, when you start with x naught, x1 will be equal to x naught into 1 plus lambda delta t. x2 will be equal to x1 into 1 plus lambda delta t. Right? As you can see, here you have number, this thing will have 1 plus to that number. So we can just but what is x1? x1 is x naught into 1 plus lambda delta t. Therefore, x2 will be equal to x naught, substituting 1 with this, x1 with this, you'll get x naught into 1 plus lambda delta t whole squared. Okay, fine. So by the same principle, you have a 2 here and you have a square here. You can now iterate to any n number you want. So it will be xn is equal to x naught 1 plus lambda delta t raised to n. Now the step size delta t is fixed. T naught plus n times delta t is tn. Here I have written something. I hope you are able to appreciate the importance of these two statements. Tn follows an arithmetic progression, right? But xn follows a geometric progression. So even if the initial value of t naught is equal to 0, here, if t naught is equal to 0, tn will continue to be non-zero. Tn will be equal to 0 plus n delta t. So tn will be n delta t. But x naught must be non-zero. In this case, x naught is equal to 1. Otherwise, if x naught were to be equal to 0, then 0 into whatever n you want to multiply it with will not matter. Xn will always be equal to 0. So x naught is equal to 1. You can see this is multiplicative progression and this here is additive progression. Additive as in arithmetic, multiplicative as in geometric. Simple interest follows arithmetic progression, compound interest follows geometric progression. Banking terminology. Okay, so I'm writing x naught is equal to 1. So x subscript n is equal to 1 plus lambda delta t whole thing raised to n. Okay. And Tn will be equal to n delta t because T naught is equal to 0. Now, we are saying lambda is a negative number. Here, I have said. So if lambda is a negative number, now you follow this point with absolute attention. All of you, full care. If lambda is a negative number, since lambda is a negative number, we are saying that as t goes to extremely large values, as per our analytical solution, if lambda is a negative number, if t goes to extremely large values, then x will tend to 0. Fine. Our numerical algorithm should reflect that fact because the analytical result must not conflict with the numerical result. There should be a good match between the two. So here's our numerical. This is the numerical equivalent of this formula, e raised to lambda t. X is equal to e raised to lambda t, and this is the numerical equivalent of that formula. Okay, so when Tn goes to infinity, now you follow this thing. If Tn goes to infinity, n must go to infinity because Tn is equal to n delta t. But delta t is a fixed step size. Delta t is not changing. That's a constant of the system, a fixed parameter of the system. Not, I shouldn't use the word constant, fixed parameter of the system. So if Tn has to go to infinity, n must go to infinity. Okay. So since lambda is less than 0, when Tn goes to infinity, n goes to infinity, and as a result, xn will have to go to 0 as per our analytical result. Now you notice something. There is a problem with the numerical integration. This is not going to happen all the time. This can only happen. This can only, I've written this thing in the uppercase with an underline to stress its importance. This can only happen when n goes to a very large number. This convergence of xn towards 0 can only happen when 1 plus lambda t, the modulus of it, will be less than 1. What do I mean by that? Suppose if this number were to be 2, right? 2 raised to a very large number, 2 raised to 2 is 4. 2 raised to 10, I don't know what is it, 2 raised to, I mean, you are the numeric binary people. 2 raised to 2 is 4, 2 raised to 3 is 8, 2 raised to 6, 4 is 16, 2 raised to 5 is, what is it, 16 into 2 is 32, 32, then 64, like that. If this number is greater than 2, greater than 1 point, any number, this convergence towards 0 will not happen. Similarly, if this thing were a negative number, let us say minus 2, right? Minus 2. You square it, you get 4. You cube it, you'll get minus 8. You take any number, n, plus or minus doesn't matter. This number, xn, will not go to 0. It will either be a very large negative number or a very large positive number, but not 0. For convergence to happen, this 1 plus lambda t must have a modulus value of less than 1, modulus of less than 1. Otherwise, you'll have the violation of the convergence when, I made a slight error over here, lambda delta t will be positive. If lambda delta t is positive, 1 plus a positive number will be a number greater than 1. If lambda delta t is less than minus 2, remember, negative numbers are actually smaller, become smaller when the value of the number becomes larger, right? Minus 3 is less than minus 2. Minus 5 is less than minus 4, like that. So you can only get a convergence. This should be lambda delta t greater than equal to 0 and lambda delta t less than equal to 2. Suppose you have got minus 3, which is minus 3 is less than minus 2, less than equal to minus 2. Suppose you've got a number minus 3. 1 minus of minus 1 plus minus 3. Lambda delta t is minus 3. 1 plus minus 3. What will it give you? It will give you minus 2. Minus 2, higher powers, you'll get very large numbers, either with a plus sign or a minus sign. If n is an even number, you'll get a positive number. If n is an odd number raised to an odd power, you'll get a negative number. Whatever it is, but it will not go to 0. So this convergence condition will be violated if lambda delta t becomes larger than 0 or larger than equal to greater than equal to 0, or lambda delta t is greater than less than equal to minus 2. Right. In the correction set of notes, this greater than equal to and less than equal to signs are there. So just please make a note of that. What about convergence to 0 as per your expectation from the analytical result? What will happen when you want to have that? This number the modulus must lie between 0 and 1. Take a simple example. 1 divided by 2, which is half, 0.5. Modulus is lying between 0 and 1, 0.5. We take a simple number, midway between 0 and 1. 0.5. 0.5 is 1 by 2. 1 by 2 squared will be 1 by 4. 1 by 1 by 2 cubed will be 1 by 8. 1 by 2 fourth power will be 1 by 16. As you can see, if the number is a fraction as in between 0 to 1, that kind of a fraction is a fraction less than 1 in absolute value, then for larger and larger powers, the number will become progressively, xn will become progressively smaller and smaller. Therefore, for stable convergence, as per your expectation, the criterion that you have to apply on this 1 plus lambda delta t is that it must lie between minus 2 and 0. This is a simple example, but it should tell you what is the importance of a judicious choice of step size. Now let us see. This is an inequality formula, and we have said lambda is a negative quantity, right? Here I've said, I've written it, if lambda is a negative quantity, just remember that fact, lambda is a negative quantity. So now what I'm doing here is that I'm multiplying this equation throughout with -1. So it will be +2, and this will anyway be 0, and this will be minus lambda delta t, but when you uh, multiply an inequality with a negative number, the arrows change in the opposite direction. So it is like saying -2 is less than -1. But when you multiply that inequality with a -1, then it will become +2 is greater than +1. So that is why whenever you're dealing with an inequality and multiplying the inequality with a negative number, the arrows have to flip direction. So that is what has happened. 2 minus lambda delta t is greater than 0. Remembering that lambda is actually a negative quantity, therefore minus lambda is a positive quantity. Thereafter, what we do is that we divide this equation, this inequality by minus lambda. So 0 less than delta t less than 2 by minus lambda. That is the criterion for stable convergence. Let us look at an example. This example is very important. What is the example? Lambda is equal to minus 100, negative number. Tn is equal to 0.2, right? Tn is equal to 0.2. Delta t, we shall have to choose this delta t. This delta t must be chosen in such a way that it should be positive. Of course, it's a time step. You have to increase in time. So positive, of course, but how positive? Its upper limit should be less than 2 times by minus lambda. That is important. So I'm asking you to carry out an integration where Tn is equal to 0.2. Delta t I have not specified for you. You shall now see what happens. Now, lambda raised to -1, I'm defining as a new quantity called tau. You'll follow this discussion carefully, you'll understand. Lambda raised to -1 is tau. And lambda is equal to -100. Therefore, 1 by -100 will be minus 0.01. Okay. Now, the actual solution coming from the integral result is e raised to lambda t. I'm sorry, I made a mistake over here. It should be plus. I mean, there should be no minus over here. E raised to lambda t. Right, that is the integral solution. So when t is equal to 0.2, e raised to lambda t will be e raised to -100 into 0.2, and that should be e raised to -20. E raised to -20 is 2.06 into 10 raised to -9. So when Tn is equal to 0.2, as here, the actual integral solution should give you this answer, 2.06 into 10 raised to -9. This, we are using this equation, the integral solution here, to find this thing. Now, what if you take the wrong kind of step size and start numerically integrating? That is why I'm asking you to be attentive to this discussion. Please follow carefully. Right. Tn is constant at 0.2. Tn is equal to n delta t. Meaning if Tn is fixed, you now have the freedom to choose either delta t or n. If you choose one, the other will be fixed immediately. And xn is equal to 1 plus, let's see, here you have got 1 plus lambda delta t by raised to n, right? So lambda is 1 upon lambda is tau. So instead of lambda delta t, I'm writing as delta t by tau, whole thing raised to n. This is the formula. Substituting for lambda in lambda delta t, we write this, delta t by tau raised to n. Now you follow. Tn, I'm saying, you don't have any choice. It is fixed at 0.2. Okay. You can now take delta t's as per your choice. Arbitrary. You have no clue, so you're just taking delta t to be equal to 0.1. Okay, fine. If delta t is equal to 0.1, then by this formula, Tn being equal to 0.2, n will be equal to 0.2 by 0.1, that is equal to 2, right? And tau is fixed. Tau is minus 0.01 and delta t is 0.1. So 0.1 divided by minus 0.01 will give you minus 10. Okay. What about xn? Now you follow the disaster that has happened. Xn is equal to 1 plus delta t by tau. Delta t by tau is minus 10. 1 minus 10 is 9. N is equal to 2. 1 minus 10 is minus 9. I'm sorry. 1 minus 10 is minus 9. Minus 9 raised to n. N being equal to 2. Xn is giving you 81. Whereas in actual fact, the real answer is 2.06 into 10 raised to minus 9. Let us now see what is happening. If I say, okay, I think we have made a mistake. Our step size is too large. We should reduce the step size. But you're still clueless as to what should be a small enough, good enough step size. So you're taking delta t to be 0.05. If delta t is equal to 0.05, Tn is 0.2. So n will be 0.2 divided by 0.05. N will be equal to 4. Okay. N is equal to 4. Now, delta t is again, I'm sorry, delta t is 0.05. 0.05 divided by minus 0.01, because that is tau. Delta t by tau will become minus 5. Delta t by the fixed value of tau here will give you minus 5. You think that now things may be better because earlier you had taken a large step size of 0.1. Now you have taken a step size of 0.05. Okay. So you are happy. Put this number. Let us see what is delta t by t tau. It is minus 5. 1 minus 5. Here, 1 minus 5 is minus 4. Minus 4 raised to 4. Fourth power. 4 into 4, 16. 16 into 4, 64. 64 into 4, 256. It's become even more than what it was earlier. You were hoping that with the reduced step size, you would be going towards a convergence. It should be less than 81, but no. It's become 256. Whereas the real answer is 10 raised to minus 9, 2 into 10 raised to minus 9. You would be, let's see, then you are saying that, okay, let me now take a smaller step size of 0.02. Delta t is 0.02. If it is 0.02, Tn being equal to 0.2, 0.2 by 0.02 is 10. That is your n. And delta t is 0.02 divided by tau will give you minus 2. Okay. So 1 minus 2 will give you minus 1. And minus 1 raised to 10 will give you 1. Still no good. Your answer is 10 raised to minus 9. You are experiencing wild fluctuations, 81, 256, 1, all sorts of things. Next, you reduce this thing even more. 0.01 delta t. N will be equal to 0.2 by 0.01, 20. Okay. Delta t is 0.01. So 0.01 by this tau will be minus 0.01. So that will be 0.01 divided by minus 0.01 will give you minus 1. So 1 minus 1, 0 raised to 20, although you shouldn't talk about raising the powers of 0. But whatever it is, 1 minus of 1 will give you 0. So again, your xn has collapsed to 0. It shouldn't be 0 either. It should be a small number, but it's a small number, but close to 0, tending towards 0, but not 0 exactly. This is too good to be true. It should happen only when Tn is infinite, right? But here you can have it, you are having it happen at finite values. Now you go by a factor of 10. 0.01 you now take as 0.001. 0.001 is your delta t. Tn is 0.2. 0.2 divided by 0.001 is 200. Okay. Delta t is, but delta t you have taken 0.001. That divided by tau will be minus 0.01. So minus 0.1 is the ratio that you get. 1 minus 0.1. Now you all follow extremely carefully. Ladies and gentlemen, all of this thing, 1 minus 10 was minus 9. 1 minus 5 was minus 4. 1 minus 2 was minus 1. 1 minus 1 was 0. That's also a bit of a disaster. It should be greater than lambda delta t should be greater than equal to 0. Not even 0 will work. Now you have got 1 minus zero point 0.1, which is zero point 0.9. It has become less than 1. Now you raise this thing to 200. Zero point 0.9 raised to 200 will give you something that is more reassuring. 7 into 10 raised to minus 10, which is zero point 0.7 into 10 raised to minus 9, off by a factor of 3. 0.7 and 2. It's just like 3 times zero point 0.7, like 21. 21 by 7 is 3. So now you are getting a convergence. What is the moral of the story? Moral of the story is delta t has to be, I told you, less than 2 times by minus lambda. Lambda is equal to 100. Minus lambda will be 100. 2 by 100 will be 0.02. 2 by 100 will be 0.02. All of the step sizes that you took, no, sorry, 2 by, yes, 2 by 100 will be 0.02. So all of the step sizes were comparable or something like that, right? You have to do it, take it smaller than 1, much smaller than that. And so here you have it, this is 0.001. Look for the natural time scale in the problem. Take a step size that is about significantly less than that, about 10 times less than that. Whenever you do numerics, that should be the key. Here, the natural time scale in the problem is 1 upon lambda. You see x here and x here. You have t here, so this thing will be 1 upon t. Lambda has the dimension of 1 upon t. So lambda is setting the natural, 1 upon lambda is setting the natural time scale in the problem. That's why I'm defining it as tau. And one tau is equal to my, modulus, that is taking the absolute value, is 0.01. So your step sizes should be significantly less than that, right? So this is 10 times less than that. And so you're beginning to have a convergence. I've written some remarks over here. Please follow. Remarks. Small delta t by tau increases accuracy, but reduces efficiency. What do you mean by that? Just see this thing. You've taken a step size 0.001, but how many steps do you have to take now? 200 steps to go the same distance from 0 to tn, which is equal to 0.2, cover the distance of 0.2 in time. You have to take 200 steps, right? Whereas if you take a large step size, you can afford to take small number of steps. Step size is delta t, n is the number of steps. So small delta t by tau will increase the accuracy but reduce the efficiency, because now you'll have to do more work. Iteration will be more. So you have to optimize between efficiency and accuracy. That is the principle of good programming. I used to long ago, listen to me carefully. Long ago, I used to work in the R&D of a seismic processing company. They used to do geophysics. So there we used to work on Fortran coding, 10,000 lines of coding. Fortran, you all do C and Python and all that. I don't know those languages, but Fortran I am familiar with. So there you have to offer your service to the customer, and you'll be charging the customer according to your programming time. So programming time is money. If your program runs for too long, then you'll have to your customer will have to pay for that. So your customer may not like that. But at the same time, if a program is too short, then accuracy may be affected. Your customer is not going to like that as well. So a good programmer will have to optimize between the accuracy, the kind of quality of the product that he or she will have to give the customer. But at the same time, the customer can't be kept waiting for too long, right? There is always an optimization between efficiency and accuracy. Economics says that. Somebody is making a very good product, but this somebody says to you that, sir, you shall have to wait for 1 year to get the product. You'll say that, okay, fine, for my purposes, I need not have such a very good product. An optimized performance of an equivalent technology will do. Somebody says that within a week you'll get the delivery of your product, you'll be fine. You just do some market survey and check that, okay, their product may not be as glittering, as efficient as the first one, but for your purposes, you'd be happy. So that's the mass market. So In the long run, you'll be working in the industry as programmers. You should be mindful of this fact, right? Okay, so here, this one last point I'll make on this thing, binomial expansion. This thing, you see, this whole business, xn is equal to 1 plus z raised to n, where z is delta t by tau, right? Why are these large, wild fluctuations happening? Because this z is becoming large. Delta t by tau is becoming large. How large? If you see in the first case, here is minus 10, this z is minus 10, and n is 2. So basically, it is a competition between the smallness, I mean, this z and this n. If you do a binomial expansion of this thing, the most dominant term for minus 10 and 2 is z squared. The others are small. You can see z squared will give you 100, then the 2z will give you minus 20, and this will give you 1. This is 1 plus z squared will be 1 plus 2z plus z squared. That is what it is, just algebra. So the dominant contribution comes from the highest power. Highest power is 100, and the actual result is 81. So the most contribution has come from the 100 is close enough to 81. So the most contribution has come from the most dominant power. Next, you take minus 5 and 4. Why did this thing suddenly become so large? This is the full binomial expansion. The dominant contribution is coming. I mean, if you write this thing in full, it will be z raised to 4 plus 4z cubed plus 6z squared plus 4z plus 1. The dominant contribution, because this number z is greater than 1, modulus, that is greater than 1. Minus 5 is actually less than 1 because this is a minus sign, but I'm talking about the modulus, particularly when it has got an even power. So the even power will kill the difference that may arise because of a plus minus sign business. So the actual answer is 256, and the dominant contribution to that comes from 625, which is minus 5 raised to 4. Right, 5 into 5, 25, 25 into 5 is 125, and 125 into 5 is 625. Ignore the minus sign because it's an even power. So 1 plus z raised to n for z greater than 1 is dominated by the highest power, which is z raised to n. For an even value, this is more so true. And so this thing, z must be less than 1. If z must be less than 1, then you have to be careful about setting the value according to the parameters of your problem, which is, in this case, lambda. Anyway, I shall now just go on to the last part of these notes. Please just give me 2 or 3 minutes extra today so that I should be able to finish it. Okay, please just give me 2 or 3 minutes extra today. Numerical, this is one last topic on the math. Then next week onwards, we'll start the physics discussion. Numerical integration of non-autonomous equation, because this will also be necessary for your lab work. So that's why I just want to take non-autonomous equation in the lab. I refer to these notes. Autonomous is dx dt is equal to fx. Non-autonomous is dx dt is equal to f of both time and x. But the initial conditions, that structure remains the same. At t equal to 0, at t equal to some value, x has got some initial value. Okay. You carry out a Taylor expansion of the foregoing non-autonomous equation about t naught x naught. Taylor expansion is not a problem. X is equal to x naught into dx dt at t naught into t minus t naught plus 1 by factorial 2 d2x dt squared at t naught, because it's about t naught and x naught that you're carrying out the expansion, t minus t naught squared plus higher orders, cubic orders. But we shall not look into cubic orders here. Just the first order will be fine. Second order will be fine. Okay. Now, dx dt is at t naught is f t naught x naught, f t naught x naught. And d2x dt squared is df dt at t naught, right? You just take a derivative of this thing on both sides with respect to t. df dt is equal to t naught. Now, df, f depends on both t and x. So df, partial differential equations, a little knowledge of that which you would have studied in your calculus course will be useful here. df will be equal to del f del t into dt plus del f del x into dx. In fact, you would have done these things when we talked about gradient divergence, the del operator and all that. It's the same thing here, except that it's got two variables. Del f del t, mathematically it's the same thing, dt plus del f del x dx. When we have this thing, we are dividing this equation throughout by dt. So df dt is equal to del f del t plus f YF, because dx by dt, whenever we divide throughout by dt, this dx dt will be f. So that will be f del f del x. Okay. So we shall substitute this thing in this equation by f, and d2x dt squared will be df dt, and df dt is equal to this thing. We shall substitute d2x dt squared by this in this equation, and we can recast the Taylor. Why are we doing all this? Because a priori we do not know what is x, the dependence of x and t, right? Beforehand nobody, but we have been supplied the function f. Therefore, for all these fixed coefficients in the Taylor expansion, we convert everything in terms of f, and then knowing the form of f as it depends on t and x, we can calculate these coefficients, this and this. So that is the whole exercise. F of t naught x naught is very well given to you. So by Euler's method, the first part is very simple. And the second part is 1 by factorial 2 del f del t plus f del f del x t naught x naught. That is, we substitute this thing, t minus t naught squared. Okay. And then the next thing is that by Euler's method, we retain only the linear term, meaning this t minus t naught, not the quadratic term, second term, and we get x is equal to x naught plus f t naught x naught t minus t naught, which can be generalized for a step size of t minus delta t is equal to t minus t naught as, you just see this thing, whatever you did earlier in the Euler method, it's the same thing, except that the argument of the function f now picks up an extra independent variable tn. So that is Euler's method. Xn plus 1 is equal to xn plus f tn xn. Delta t is equal to delta t plus, and delta t is equal to tn plus 1 minus tn. And if we account for the second order term, this thing, the second order, this is the last point. I'll just give me a minute, I'll finish it. If we account for the second order term, we get the same thing here as in the, this part is the Euler, the linear part, right? The Euler part, delta t. Then here what will you have? 1 by factorial 2 is 1 by 2. Del f del t, f del x, del f del x, you calculate at tn xn, t naught x naught will be tn xn on the right hand side, and this thing will be delta t squared. T minus t naught is delta t squared. So delta t is equal to tn plus 1 minus tn is a constant step size. All the values on the right hand side are fixed at tn xn. So you know all the values on the right hand side. You'll start with the initial value of t naught x naught as will be supplied in your question problem set, and then iterate to x1. And tn plus 1 will be known. I mean, t1 is just t naught plus delta t. Like that, you go on. So this is the basic idea of non-integration of non-autonomous equations. So with that, as I said, I needed 2 minutes extra. It's 1:17 p.m. now. I shall stop this discussion. You have any questions? Please just wait for 2 minutes. I'll just issue some instructions. Please just wait. So next Monday we have a lab. I'll just give you an extra lab problem sheet, and within this weekend, I will send you, by maybe by today only, I will send you an email. The email, you should respond to that email. Don't create your new email thread. You should respond to that email to state your preference